Right, section 211, the last section, is about the mobility of these chair conformations and how these chair conformations actually exist. All right, we're going to talk about something called a ring flip. All right, and we'll talk about why it's important. So if you look at the chair conformation that we've been doing, all right, we have the axial hydrogens. Oh, I'm sorry, I just put an equatorial in there. Well, we'll put the equatorials in too. The axial and the equatorial hydrogens. Okay, and you have your axials. I'm going to circle just the axial hydrogens. Okay, and then I forgot the one right there. I'm trying to show in 3 dimensions behind. All right, so the axial hydrogens are the ones that are going up and down. Okay. Now, what a ring flip is exactly what it sounds like. You flip the ring. What happens is that this carbon here comes up, and this carbon comes down. I'm not flipping the molecule over. I'm actually flipping the bonds. Now, if you have a model set, this will make a lot more sense. It'll be a lot easier to see. Like I said in class, I'll make models, and we'll be able to see these. It'll be a lot easier. Okay, but what you do is you flip them so that this carbon right here now is at the top, and the other carbon now is at the bottom. Okay, so this carbon's at the bottom. So what does that do? What that does is when you do a ring flip, every hydrogen completely changes its position. So what was axial? Okay, so if it was axial in this molecule, it becomes equatorial in this molecule. So now your circled hydrogens now are all in the equatorial position. Okay, and like I said, the best thing to do is to actually make this molecule, use them as different colors and flip them, and you'll see that all of the circled ones on this molecule become all equatorial in this molecule, and all of the axial and all the equatorial molecules on this molecule now all become axial. So these hydrogens now are the non-circled ones, and those all become axial. So what was one position in one molecule becomes the exact opposite, and all of them become the exact opposite. Okay, so that's what happens when you do a ring flip. So why is this important? Why do we even care about this? All right, let's take a mono-substituted cyclohexane. Let's say we take a methyl cyclohexane. Okay, there are 2 chair conformations for this molecule, 2 chair conformations. Okay, one of them is a stable conformation, and another one is an unstable conformation. Okay, so let's look at it. Let's first look at a chair conformation. And I'm going to just arbitrarily put the methyl group in the axial position, because technically the methyl can also be in an equatorial position. Okay, you do not want large groups in the axial position. All right, large groups should not be in the axial position. Okay, large groups are more stable in the equatorial position. Okay, so you want this methyl group where the hydrogen is. So what you want to do is you want to ring flip it. Let's see why. The reason is something called 1,3-diaxial steric interaction. Pretty fancy, huh? Well, let's see what it is. It's exactly what it sounds like. All right, 1,3. So what happens is this methyl group sterically interacts with the other axial positions on that molecule. So you have these 2 hydrogens, it's interacting, so this kind of, that symbol right there shows an interaction. Remember, your carbon here actually has hydrogens that are all sticking out of it. So those hydrogens are interacting with these other hydrogens. Okay, that's very unfavorable. So you do not want your methyl group in the axial position. What you want to do is ring flip this. And what that does, remember, if you ring flip it, whatever was axial now becomes equatorial, and whatever was equatorial now becomes axial. Now your methyl group is actually sticking out. All the hydrogens are sticking away from all the other molecules, and this is the much more stable molecule. Stable, unstable. So to alleviate these diaxial interactions, you want the biggest groups, or if you have more than one group on your molecule, you want the majority of the groups to be in the equatorial position. So that's why this ring flipping is very important, because it puts your molecule from a least stable molecule to a more stable molecule. So this is actually how methyl cyclohexane actually exists in nature. The methyl group is sticking out in the equatorial position, and you have your cyclohexane in the chair conformation. Now, what happens when you have more than one group on your molecule? So let's take a cyclohexane, okay, and let's take the let's take trans dimethyl cyclohexane. Okay, this is trans dimethyl cyclohexane. Now, this is very important to note. This is very important. Let's start it. Okay, cis and trans have nothing to do with axial and equatorial. They are two different concepts. They don't even correlate with each other. Okay. So let's talk about this is a trans molecule. I think during lab or homework you'll probably do the cis. You'll probably do the trans again too. So let me draw the two chair conformations for this molecule. Two chair conformations. Because everything has two chair conformations. Okay? Because you can ring flip it. Okay, so here's a chair. All right, let's call this carbon 1, carbon 2, carbon 3, carbon 4. All right, we'll call this carbon 1, carbon 2, carbon 3, carbon 4. All right, I'm going to put a methyl group, so I have an axial position and an equatorial position, and an axial position and an equatorial position. Fortunately, I kind of ran out of room there. Let me redraw this. I'm going to scoot it over. Let me put on pause. I'm going to redraw it. Okay, so here we have it redrawn. I'm going to have the axial, equatorial, axial, equatorial. All right, I'm going to arbitrarily put the methyl group up here. So that means the hydrogen is going to go here. Now, this molecule is a trans molecule. So what I have to do is I have to put the other methyl group in the appropriate place so that these molecules are trans. Okay, that would be that the methyl group has to go right here. All right. If I put the methyl group in where the hydrogen is, that would have been the cis molecule. And why is that? You have to look kind of at imagine that this molecule is flat, and notice that this methyl group and this hydrogen are on the same side. If you kind of look at it sideways, you can see a little better. And this hydrogen and this methyl group are on the same side. And so that means my two methyl groups are opposite of each other. That's how I know that I have the trans molecule. Important that you realize how to draw cis and trans. And axial and equatorial have nothing to do with it. It's just a coincidence that both of them are axial. You might have another molecule where you draw the cis and they're both equatorial, or one's equatorial and one's axial. All right, this will start making more sense when you start doing more problems. Okay, well, what's the one thing that you notice about this molecule? What you should notice is that both methyl groups are axial. And what did I just say about axial? Bad. Axial, bad. You don't want your big groups axial because they interact with the other axial hydrogens. You have a steric interaction here. So if I were to ring flip this molecule, what would it look like? Well, this methyl group, all right, will start moving up to the equatorial position because it's axial here, so it becomes equatorial here, and your hydrogen goes the axial. In the other case here, your methyl becomes equatorial and your hydrogen becomes axial. Okay, so remember, this is carbon 1, this is carbon 4. This is carbon 1, this is carbon 4. So now notice both methyl groups are what? Equatorial. This is good. This is bad. Okay, so this is the stable conformation. That's the most stable conformation that trans 1,4-dimethylcyclohexane exists in. And this is actually how the molecule is going to exist. But understanding how to do this ring flip is very important.